Okay, hello. We're all going to have class in one line. Does that sound good? All right. Hi, in Zoom. Thanks for joining us today. We have a lot of reactions that we're going to talk about today. I'm going to add one new thing in class, but most of what we're going to do is kind of review what we've done already, because I'm very aware that what I gave you guys for today was a lot. It was a large heaping spoonful of reactions. But what I want you guys to kind of see is how all of those things tie in together. So the reason that that bridge had a whole lot of questions on it was my hope is that by the end of today, you'll see how all of that stuff is not really 12 different unrelated reactions. It's really a couple different pots of nucleophiles and a couple different pots of electrophiles. And they react together more or less in like 6 ways instead of 50 ways. So we'll relate this back to what we did on Friday as well. So let's start back on Friday. What we're going to do today is talk through kind of in broad strokes what we did previously and then the reactions for today. And then we're going to move to the bridge, talk about which reactions fit, and we'll kind of go back and forth. So we'll get to all of those things, but we'll do it kind of chunk at a time, because I know that was just kind of scattered and random. Your quiz is going to be scattered and random, and you won't know exactly where you are starting. They're not going to go like chronologically or anything like that. But let's flash back to Friday really quickly. And so when we did this on Friday, we weren't talking about carbonyls with leaving groups attached. We were just straight up talking about carbonyls. So an aldehyde looks like this, where a ketone has an R on both sides. So we're just thinking in general about aldehydes and ketones. So what kind of nucleophiles, let me rewind, aldehydes and ketones are electrophiles. Everybody good with that? The carbonyl is an electrophile. And of course, electrophiles react with nucleophiles. So we could combine this with a lot of different possible types of nucleophiles. All right, so what kind of nucleophiles reacted and gave you a product when you combine them with aldehydes or ketones? We kind of lump them into this new category. Give me one example, or LAH is one of them, yes. So lithium aluminum hydride is like H-. It is a fiercely strong nucleophile. So stronger than any of our previous nucleophiles that we've used. H- is really unstable, right? So high energy, so very, very reactive. Right, so we classify these kind of as fiercely strong nucleophiles. And we had really 2 general categories, but a couple specific ones. So lithium aluminum hydride is great. Lithium LiAlH4 or just LAH. That just acts like H-. Also sodium borohydride, which is very similar, NaBH4. Both of those guys just act like H-, and H- is really unstable, so it's really, really reactive. So these are fiercely strong. The other ones acted like carbon with a negative charge, or R-. We had 2 of these. One of them is old, one of them was new. Anybody remember what these are? MG. Yep. So Grignard reagent, MgX, usually MgCl. And then the other one is organolithium. But in both cases, they are carbons bound to metals. So the carbons have the extra electron density because they're more electronegative, and the carbon acts like a negative charge. So both of these are fiercely strong nucleophiles. So it turns out that while carbonyls of ketones and aldehydes are electrophiles, they don't just react with any nucleophiles, because a lot of the nucleophiles would attack and then just go backwards. These guys attack and do not go backwards. So these were the ones that you guys put stars on for your bridge assignments on Friday. They go forward and that's what they do. So your hydride would attack the carbonyl, kick electrons up. And so for the top one, you would get O- and whatever you had over there already, plus a new hydrogen. So this would be new right here. And if you attacked with a Grignard, you would get something similar. You just kick the electrons up the same way, attacking that electrophile. So if you attacked with that carbon with a negative charge, you would get carbon attached down there. So there was something new added on. We're not going to revisit that beta position and all of that good stuff. You should review that. But this is largely the main big picture. is that those fiercely strong nucleophiles would attack a ketone or aldehyde and give you something new. So this is not new. You can write it down if you want to, but this is basically shorthand your notes from Friday, which we will need to kind of start from this. All right, so what if we added kind of a routinely strong nucleophile? Like, let's say, O minus, I don't know, OH minus. So that is a strong nucleophile. This was kind of the second question in your bridge from Friday that didn't end up with a star. Theoretically, this can attack an electrophile and kick electrons up. But this is what we would get. So feel free to not write this down because it's not actually going to get us anywhere, but more see if you can kind of follow along with what we're doing here. So that's a little sloppy, but we would attach an OH minus. So going backwards, if we use the hydride, we start with an H minus and we end up with an O minus. What's more stable by a lot? O minus. So this is definitely going to go forward to the more stable thing, which is the product. All right. If we start with a C minus and we attack, we get an O minus. What's more stable, C minus or O minus? O minus. So check electronegativity, check the periodic table. Oxygen is to the right. Oxygen is way more stable with a negative charge than carbon is. And that's still true. That's stuff from last semester. That's still true. So that's the reason why these guys go forward. With this reaction, we're starting off with an O minus and we're ending up with an O minus. What's more stable? It's a trick, it's about the same. So entropically, it's not favorable to put multiple molecules together if there's no other reason that they should be. So really what happens is this ends up being kind of like a pointless slingshot where you kick electrons up to the O and they just come back down and kick back off what you started with. And so this whole thing just goes backwards mostly. And for the most part, we would just kind of say that this is no reaction. Because you don't really get a product, you just kind of make something and then it immediately falls apart. So really, it's just like throwing something up in the air and it just falling back down again. You're not getting anywhere. You're not really accomplishing anything. All right, and if we started with a ketone or aldehyde and added a weak nucleophile, do you think anything would happen? No. So like water, if you put water in, it's not going to attack anything. Thank God, right? We're made out of water. If water was a strong nucleophile, then we would be attacking ourselves constantly and fall apart. But no, water's neutral. It doesn't really do much of anything. It's pretty stable, usually a product. So really, if we're looking for what is going to attack a ketone or an aldehyde, this is going to be a trend we're going to talk about. I'm going to ask you guys this same question a whole bunch of times today. What attacks a ketone or aldehyde and gives you a product? Fiercely strong nucleophiles. So your hydrides and basically your C minuses, right? And that's it. Everything else just kind of goes backwards. All right, so let's look at how these fit into our bridge assignment for today. Need to stop sharing that. Any questions out in Zoom about that? All right. All right, so let's look at the ones that started with a ketone or an aldehyde. So the first one started with a ketone. We had an acid chloride. Then the third one was an aldehyde. So I'm just going to star all the ones that were ketones or aldehydes because this is stuff from last week. All right, here's a ketone down here. So we'll look at that one. Going over to the right column, I've got an acid chloride, I've got an ester. Oh, here's another aldehyde, so we'll do that one. Got an acid chloride, an ester, and an ester. So let's just look at those that were ketones and aldehydes. Because what attacks a ketone or an aldehyde and goes forward? Fiercely strong nucleophiles. All right, so here we have O minus. Is that a fiercely strong nucleophile? Is that a H minus or a C minus? No. So will this attack your carbonate?
No. Yes.
Well, it's a great, so is it gonna give you a product?
No.
Not really. Will it attack? Sure, but then it just goes backwards again. So is it gonna give you really anything you can collect at the end of the day? No. So you could draw this out, but if you draw it out, you should write out, it's definitely gonna go backwards, or there's just no reaction here. I'm not going to intentionally try to trick you on a quiz by giving you things that I know won't work, but But I wanted you to think about what does work and what doesn't work, especially when we get to the acid chlorides, where some things attack twice, some things attack once. That's all about what attacks ketones or aldehydes. All right, so there's no reaction there. Sure, it could attack. All right, so don't draw this mechanism, but I want you to kind of see how this relates. If it did, it would do this and go back up, but then it just come back down again and just kick that thing off. So that's all silly. I'm going to actually erase all that. But do you see kind of that it just basically slingshots up and then just kicks itself back off again? So the idea of kind of throwing something in the air and having it come back down again, really that's all that's happening. All right, so moving on down, lithium aluminum hydride. If you see this, LiAlH4, I would just immediately rewrite it as H minus. Is that going to attack? Yes. So it attacks your carbonyl. Hopefully you've seen this. Everything this week, everything on this quiz is going to attack your carbonyl. This is always what's happening because carbonyls are electrophiles. That's actually the name of this week is carbonyls as electrophiles. So this is what we're going to see. All right, so that goes ahead and goes on up. That will result in, you're going to have an O minus at least for now. We have one left over H and we have a new H. So a lot of today is looking at that kind of slingshot mechanism. Why don't these electrons come back down and kick something off? No, you got the right idea. So there is a lot of H minus, but in some of the reactions we see today or for your bridge, this is what happened. Don't write this down, please. This is not happening. But if these electrons swing back down, it can't just do that because that would make 5 bonds to a carbon, right? So what are its options for kicking off of this carbon? Hydrogen, hydrogen, or carbon? Are any of those remotely stable with a negative charge? No. So are any of those remotely good leaving groups? Not at all. So there's no reason that it can come back down again. So it's stuck. So that will not ever happen. And that's why we're done. So there could be a second step where we protonate this. I'll put this on the quiz. But for the bridge, I just wanted to consider just the nucleophile. So some people added in, then we would protonate it. Yes, and make it into an OH and you'd be done. So, but that's it.
So that's how we know if we need to do excess or 2 steps by determining if it's a good leaving group or not.
Yeah, exactly. So the idea of, and we'll get into this in a minute, but when you've got a chlorine, you have a good leaving group attached to your electrophile. And that's when you have something to kick off. At this point, there's nothing to kick off. And so we didn't even think of this idea of kicking anything off last Friday, which is why I think it's worth kind of going back to last Friday. There wasn't. And so there was nothing else to do. That was it. You just kick it up and you're done. All right, questions on that one? All right, so let's move on down. Here is a ketone. And we have a Grignard reagent. So a Grignard reagent, tell me how that works. What does it react like?
C.
Yep, with what charge? Yep, minus, perfect. Yes, thanks, Miguel, it's a C minus. All right, so you've got 4 charges and the one attached to the magnesium is gonna react as if it's a negative charge. So I wanted to kind of focus on that, but we'll redraw this. It's basically gonna be kind of like that thing, right there. But it is still 4 carbons, one of them with a negative charge. Is that a weak nucleophile or a strong nucleophile or a fiercely strong nucleophile? So these are our 2 fiercely strong nucleophiles. So we need to know these. All right, we've got the C minuses, Grignard or organolithium, and the H minus, lithium aluminum hydride, sodium boron hydride. Those are going to be fiercely strong. All right, so it can attack this carbonyl, kick electrons up, and we would now have an O minus up there because we pushed electrons up. And what we've added in is 4 new carbons. So numbering these can be good. I'm going to draw them out, circle them here. These are our 4 new carbons that we added. So looking at this guy and even just considering, can we slingshot back down again? If these electrons came back down here to make a double bond, my only options would be to kick off a carbon. What's more stable by far, an O minus or a C minus? O minus. So is there any reason it would ever try to kick a carbon off? No. Carbons are never going to be good leaving groups unless there's some weird reason that they'd be stable with a negative charge. And we should know that because we've seen what our leaving groups are. You guys know your leaving groups, right? Basically halogens. We have a couple other ones, but that's for the most part what we've got. So we're stuck and we're done, and that's the end. So kind of knowing when you're done is a really good place to be. All right, so the only other one we had in here that was a ketone or an aldehyde is in that second column. It's this little aldehyde right here. All right, so once again, an aldehyde is an electrophile, but what kind of nucleophile reacts with an aldehyde? Those fiercely strong nucleophiles, right? Is water a fiercely strong nucleophile? No, so is anything gonna happen? No. So we talked about back in naming that you could get a hydrate here, which would have two OHs, but all of that stuff is reversible. There is really no reaction here. Does that make sense? So kind of thinking again about ketones and aldehydes, the only thing that really directly attacks them, this was that direct addition, going straight into the carbonyl, is going to be those fiercely strong nucleophiles. We had some exceptions like cyanide did, but they were not nearly as important as those two main ones, an H- or a C-. All right, so that's stuff from last Friday. Any questions on those four? So let's go back again to today and consider kind of some of our new stuff. And most of our new stuff for today involved a carbonyl, yes, and a carbonyl electrophile, yes, but a carbonyl electrophile that had a leaving group attached. So this was a different set of functional groups. And let's look at them in more specifics. The most reactive one we kind of have a tie. It's the acid chloride, where the chlorine is your leaving group, and the anhydride, which looks like this. Anhydrides are symmetrical, but they've got kind of what looks like a carboxylic acid here. It's almost like a double ester, but what they've got to kick off would be a carboxylate. And in both of these cases, those things are pretty good leaving groups. And so you have a really, really, really reactive carbonyl. The second video was about esters. Esters are far less reactive. All right, so just kind of thinking about these guys are great leaving groups. And down here, that's part of an ester, is a pretty poor leaving group. So this is how these guys are different. They still have a carbonyl, but they're a carbonyl with a leaving group attached. So now we got something different and new. We're not gonna talk as much about the anhydrides. We don't use anhydrides nearly as much as we use acid chlorides, but they have basically identical reactivity to acid chlorides. So if you ever see an anhydride, feel free to think of it exactly like an acid chloride. But both of them fall into this pot. They're a C double bond O with a leaving group. So just like we talked about 5 minutes ago, if you've got a leaving group attached to a carbonyl, then you can kind of come back down and have something to do, something to kick off. All right, so let's consider this carbon for a second in an acid chloride. We know it's an electrophile for 2 reasons. Olivia, give me one reason why this carbon is electrophilic. It's attached to a leaving group. Good. Caleb, give me another reason why this carbon's electrophilic. Exactly, double bond O. So think of acid chlorides as basically double electrophiles. We've only really covered 2 electrophiles in all of organic chemistry. One of them from last semester was carbon with a leaving group. And from this semester is a double bond O. And so really this is both of those at the same time. So it's a super good electrophile. So if you have the top of the line, most reactive electrophile, you don't need a good nucleophile. You just need any nucleophile. And it turns out that any nucleophile will react with an acid chloride. So weak nucleophiles will react with acid chlorides. Strong nucleophiles will react with acid chlorides. Fiercely strong nucleophiles will react with acid chlorides. All nucleophiles react with acid chlorides because acid chlorides are phenomenal electrophiles. All right, so someone give me an example of a weak nucleophile. So something with neutral that has electrons. Sure, H2O, great. Water does not like to react with things, but it can because it does have electrons it can share. It's a weak nucleophile, it's a weak acid, it's a weak base, it's kind of a weak version of everything. All right, so where in here do we have an electrophile? The carbon, right? The carbon that's both in a carbonyl and has a leaving group. So your water can attack, it's gonna kick electrons up to the O, but anytime you've got these acid chlorides, they're always gonna do the same thing. No matter which nucleophile you use, they do the same thing. They kick electrons through an O, it slingshots back down again, and what will it kick off? Cl, right, because Cl is our best leaving group here. So we are going to replace the chlorine with, in this case, an OH. Technically, it would be an OH2 plus, but it would just get deprotonated and become neutral, and so it just become an OH. Sound good? So in all of these reactions of acid chlorides, and we're going to have a lot of reactions of acid chlorides, we're going to kick off that chlorine and replace it with whatever your nucleophile is. All right, so that's a weak nucleophile. Someone tell me a strong nucleophile, not a fiercely strong one, just a strong one. OH minus, great. Okay, that's going to give us the same product. So you mind if we shake it up a little bit? Sure. We're not going to shake it up too much, and you are correct. All right, let's go with, so strong nuke. Got an O minus attached to, I don't know, 3 carbons in a row. So nucleophiles attack electrophiles. And they kick off leaving groups. But first, you kick electrons up to the O, you slingshot it up, they swing on back down, kick off that leaving group. We would have now what attached over there? That's my new thing that I've joined in. Yeah, so it'd be the oxygen with all of its carbons attached. It's not going to be negative anymore because it's shared electrons, so now it's going to be neutral. Oxygens with 2 bonds will be neutral. But it's going to be all of that stuff. All that stuff is attached there. And we have kicked off a chlorine. Is there any compelling reason why these guys would attack again? First off, does water attack anything again? Water doesn't really react with anything except for our acid chloride. Do we have an acid chloride hanging around in our product? No. We made, this is a carboxylic acid. So this is just a functional group interconversion if you want. Acid chlorides can turn into carboxylic acids. Acid chlorides can turn into, what's this thing? Ester. We'll talk about, we saw esters already. We'll talk more about esters. Esters don't react with much of anything besides fierce nucleophiles. So we're done. We're done. We're good. I mean, even if this thing attacked, it would kick off the same thing and you would get the same product. So it wouldn't really matter. All right. So weak nucleophiles attack acid chlorides once. Strong nucleophiles attack acid chlorides once. And then they're done. So the new and crazy thing was, I'm going to put a little line here. What happens when we start with one of these acid chlorides and we add a fiercely strong nucleophile? And eventually you can kind of skip this and get to where you're going. But let's think about this just in terms of that same step, because the first step here is going to be the same as everything above. All right, so give me a fiercely strong nucleophile. Just pick one. LiAlH4? NaBH4. All right, you're going. Sodium borohydride. Sounds fine. Fiercely strong nucleophiles. So for example, NaBH4, which just like lithium aluminum hydride, just kind of cross it off and imagine that it's just H minus. So they're basically doing the same thing. So we've got an H minus. Is that a strong nucleophile? It is strong. It's so strong. It's ridiculously strong. It's fiercely strong. But since any nucleophile can react with an acid chloride, can a fiercely strong nucleophile react with an acid chloride? Absolutely. This is the strongest nucleophile and the strongest electrophile. Of course they will react together. They would love nothing more than to react with each other. So nucleophile attacks electrophile, electrons up, they swing back down and kick off our leaving group. And we will have replaced that chlorine with H. Fantastic. All right, so let's pause for a moment and look at where we are. So you've got a little round bottom flask. You've added some hydride. It's reacted. Will you immediately know that you have an aldehyde and be able to just say stop and have everything go to its separate sides and be done? That would be wonderful, but no. What you put into your little pot there is still there. And so it turns out that if you have any reaction that can still happen, it will still happen. You don't get to control that. So do fiercely strong nucleophiles react with aldehydes? We're swinging, we're gonna stay, I'm taking literal step backs to Friday and to 20 minutes ago. What reacts with ketones and aldehydes? Fiercely strong nucleophiles. So do fiercely strong nucleophiles react with ketones and aldehydes? Yes. What do I have here? Aldehyde. And what do I still have in my pot? So will you get another reaction, whether you want it or not? Yes, you will. So this is where that, I know that what attacks once, what does attack twice? All of that is fiercely strong nucleophiles are the only thing that will ever attack twice. The reason why is because fiercely strong nucleophiles give you ketones or aldehydes after one attack, and then they can attack ketones and aldehydes, which is what you just made. So we will get a second step, whether or not we want it, which is that your NABH4 is still there, and it will attack a ketone or aldehyde the same way that sodium borohydride or any fierce nucleophile always attacks a ketone or aldehyde. So Friday didn't stop. It keeps going. It's still true. So basically this first step was new for today, but the second step is just the old stuff from Friday, which will still happen. All right, quick recap. Are you ready? Acid chlorides or anhydrides. If you use a weak nucleophile, will they react?
Yes.
And attack how many times? Once. And you can try to memorize that or just look at the product. Do I have something that's going to react together still? No. All right. Strong nucleophiles, are they going to attack acid chlorides? Yes, and they do that. All of these do the same thing in that first step, right? They swing on in there and kick the leaving group off. But now you got an ester. Do esters react with regularly strong nucleophiles? No. So is there any reason for them to react again? No. So they're done. All right. Fiercely strong nucleophiles. Do they attack acid chlorides? Yes. And look what you'll always get. You'll always get a hydrogen or a carbon there, which means you'll always get a ketone or an aldehyde. And do fiercely strong nucleophiles react with ketones and aldehydes? Yes. So will they always attack these guys twice? Yes. And you won't be able to control it. So if you want to, you can go stepwise, or if you get really comfortable with them, have it go in again. But basically, think of what we talked about a few minutes ago, that this carbon right here of an acid chloride is an electrophile for two reasons. It's got a carbonyl, which would get attacked by a fiercely strong nucleophile, and it's got a leaving group, so it would be attacked by a fiercely strong nucleophile. So both things happen. You kick the leaving group off, and you push electrons up to the end. All right, so let's look at how those fit into our bridge assignment. Bum, 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 share screen. All right, we'll do these in blue. All right, so here is an acid chloride. We'll do that one. Here is an acid chloride. We'll do that one. This is an anhydride down here at the bottom. So what we can do is just kind of imagine that this whole part here on the right is just like a chlorine. So this will react in the exact same way. Going to the top over here, here's another acid chloride. Right, then we got an ester, we'll save that for later. Here is our final acid chloride, and then we just got a bunch of esters. So there are 5 reactions here that are acid chlorides or acid anhydrides, all of which get attacked by nucleophiles. So what kind of nucleophile attacks an acid chloride? And? Yep, and weak, and like the normal strong, fiercely strong, and weak. All of them attack an acid chloride. So if you see an acid chloride, who's going to attack it? Anybody, whatever, right? Anything. Okay, so here we go. We've got an O minus. That's a strong nucleophile, right? What's a nucleophile? Is it going to attack an acid chloride? Yes. So notice above, those strong nucleophiles that aren't fiercely strong, they don't attack ketones or aldehydes. But they do attack acid chlorides because every nucleophile attacks acid chlorides. And then back down and we kick that chlorine off. And at the end of the day, what you have done is you've kicked off the chlorine and replaced it with whatever your nucleophile was. Here it's O with benzene, it's this chunk. So with these acid chlorides, they're all substitutions basically. Technically we call them addition eliminations, but you end up at the end of the day really just taking off your leaving group, replacing it with your nucleophile. It doesn't matter if it's strong or weak or whatever. All right, what about lithium aluminum hydride? Is that a nucleophile? Yes. How nucleophilic is it? Fiercely strong. So will it attack? Yes. So I'm going to do this one stepwise. Nucleophile, boop, boop, kicking off my chlorine. So at least for the moment, I would get this because what I've done, much like I did above, is I'm just taking off the leaving group and replacing it with my nucleophile. But, beat me to the punch, but it's going to attack again because we have a fiercely strong nucleophile which does react with aldehydes. And what we have now is an aldehyde, so we will attack again. So after this one goes twice, I would have an O minus, and now I've added 2 H's. Once when we attack the acid chloride, and once when we attack the aldehyde that we got after that first time. Questions on that? So the reason I kind of put these in order that may have looked random. If you have an aldehyde, lithium aluminum hydride attacks it, right? You have an acid chloride, lithium aluminum hydride attacks it, but then makes an aldehyde. And so this second step right here is exactly the same as the problem above. If you have an aldehyde, it gets attacked by LAH. If you have an aldehyde, it gets attacked by LAH. Whether you started with it or you made it in the middle of a reaction, an aldehyde will get attacked by LAH. Make sense? So that's why how these things are all kind of connected a little bit. All right, I've got an acid anhydride. It acts like an acid chloride. Will it get attacked by a nucleophile? Yes, acid chlorides get attacked by all nucleophiles. So fiercely strong nucleophiles are our best nucleophiles. They'll attack any electrophile. Acid chlorides are our best electrophile. They'll react with any nucleophile. All right, so here we go. This is going to be my electrophile. This reagent here is exactly like the one above it. These 2 questions are going to have a lot in common as well, just like the 2 previous ones. I'm going to have this 4-carbon chunk as my nucleophile. I'm going to draw it like that. It's going to attack your electrophile. Electrons go up, come back down, and kick your leaving group off. You might notice that this thing is symmetrical. So if you attacked the carbonyl on the left and kicked off the right half, or if you attack the carbonyl on the left, or sorry, the right and kicked off the left half, you'll get the same thing. It'll just look backwards. But either way, it's going to be the same thing. We're going to kick off your leaving group and replace it with that new carbon chunk, which looks like this. Make sure you get all your carbons in there. Okay, what have we made? You made a ketone, and we have a fiercely strong nucleophile. We're all going to take a breath. Take a second. You ready? So from last Friday, what reacts with ketones and aldehydes? And do you have one? So will it attack it? Yes. So we will go again. And you're going to specifically attack your carbonyl, because that's the spot that's electrophilic. So we would have what is effectively two isobutyl groups attached at that carbonyl. The carbonyl isn't there anymore, it's an O minus. And now we don't have an electrophile anymore. So you can't attack a third time, you have nowhere to attack. All right, just as a thought experiment. Can these electrons swing back down and kick anything off? Can these come back down and slingshot off one of those groups? No, because they're carbons. You can't kick a carbon off with a negative charge. So again, we're going to kind of go backwards a second. Whenever you have a ketone and you add a Grignard, they react together because it's a fiercely strong nucleophile. You got an acid chloride or an anhydride, and you attack it, you'll get a ketone. And ketones react with fiercely strong nucleophiles, so it'll go again. So the second step here, in which a Grignard attacks a ketone, is exactly the same thing as we had this little old Friday stuff step above. Ketones get attacked by fiercely strong nucleophiles. It just happens that they also get made by fiercely strong nucleophiles attacking acid chlorides, which is why acid chlorides get attacked twice by fiercely strong nucleophiles. Any questions on that one? Does that make more sense than maybe it did when you were first doing this bridge assignment? Okay, good. All right, this one should be a little bit repetitive up here at the top. I've got an acid chloride. And I've got a Grignard. And a Grignard is a fiercely strong nucleophile that's in this case, it's two carbons. It's two carbons. So what will it do? Caleb, go, what's gonna happen?
So it's gonna slingshot electrons up to the opposite, back down.
Yep.
And then later.
Yep. And so you will kick off and replace that chlorine with a 2-carbon chunk. All right, are we done? Why not?
Because there is still a ketone.
Yep. You still have a fiercely strong nucleophile, so you will attack again. Bum, 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 bum. So we'll add that 2-carbon chunk on again. Well, not the same one, but another 2-carbon chunk. And then we're done because you can't bring electrons back down because there's nothing to kick off. All right. Moving on down. This is our last one with acid chlorides. Kind of halfway down that second column, you had an acid chloride plus water. Acid chlorides react with any nucleophile. Is water any nucleophile? Sure. So it'll come on in here and do the same thing. And Olivia, you're going to replace that chlorine with what? OH. Fantastic. So this is the same thing that you would get if you use sodium hydroxide. So the reason that we would normally just use water instead of sodium hydroxide, if this is what we want to make, is because what's the point of adding something that is very reactive and might burn you when a little bit of water that you can get from all the sinks in the world will do the same thing? I mean, assuming your sink works. So yeah, there we go. We're done. That's acid chlorides. All right, how are you feeling about acid chlorides? Okay, let's do esters. So to me, esters are the most kind of nuance of all of this because they're the least reactive of all of our stuff that we're using right now. So here is an ester. I put this on that previous screen, but the idea is that you've got a leaving group, but it's a really crappy leaving group. And so to kick off that leaving group, you need to have something that's really, really, really reactive. And so an ester, how is it reactive if we had to choose one of our 5 things? Acid, base, nucleophile, electrophile, leaving group. It's a carbonyl. All of our carbonyls have the same thing. Electrophile. Okay, good. This is the weakest of all of our electrophiles. At least the ones that we're going to cover for this week. So if you've got a not very strong electrophile, what kind of nucleophile do you think you'd need to make anything happen? Yes, perfect. So your fiercely strong nucleophiles will attack esters. All right, so let's pretend we don't even know. We're doing some trial and error. So again, they all do the same thing, fiercely strong. In this case, it's actually, you might remember that sodium borohydride it'll react with it. It just goes really, really slowly, because while it is fiercely strong, it is less fiercely strong than lithium aluminum hydride. So everything's really, there aren't really pockets, but we can mostly separate these things into batches. So let's use lithium aluminum hydride, LiAlH4, but any of these, Grignard would work the same way. So that thing is a ridiculously unstable, super reactive nucleophile. And where is it going to attack? Carbon, specifically the electrophile. Electrons go up, and then if they come back down again, they would kick this thing off. So let's see what we get and whether this reaction would favor starting materials or products. A new thing that we've added in here would be a hydrogen. And what we would have kicked off is an O- attached to an R group. You guys all follow? Adding in a nucleophile, kicking off a leaving. All right, so take a second and think about this. In my starting material, what was my unstable charge? H-. And in my product, what's my unstable charge? O-. Which one of those things is more stable? O-, and it's by a lot. So the reason that these fiercely strong nucleophiles are so strong and reactive is because they're H- and C-, which are our least stable negative charges for nonmetals. And so basically they're always going to react because they're always going to be the least stable thing. And so pretty much you can always turn them into something more stable. In fact, lithium aluminum hydride, we have to be so careful with that it'll react with water and just take an H off and bubble out with hydrogen gas. So if you're doing lab today or tomorrow, or even if you're doing lab next Monday or Tuesday, we're using a hydride, but we're going to use sodium borohydride instead because you're less likely to cause an explosion, right? Because it reacts with water or methanol or whatever you have. Even the water in the atmosphere, you got to keep it stored up tight. So will this go forward? You started with an H- and you turned it into an O-. Did you make it more stable? Absolutely you did. So will this go forward? Yes, because you're making a more stable product. All right, and let's glance at what we've got here. We've got an aldehyde, and we have a fiercely strong nucleophile. Do fiercely strong nucleophiles? Yes, they do. Yes, I got scooped in case you're in Zoom, but yes, fiercely strong nucleophiles attack aldehydes and ketones. Aldehydes and ketones get attacked by fiercely strong nucleophiles. Therefore, you're gonna get this second reaction. You're gonna have it attack again. So if you're keeping track, your fiercely strong nucleophiles will react with everything. They will react with esters and attack, and then attack again. They will react with acid chlorides and attack, and then attack again. They will react with aldehydes and ketones, and they will attack. But they'll attack everything. All right, so we'll still have H- hanging around, and it's still going to attack. Doop, doop. So we're going to add another hydrogen on here, and basically this thing is going to go twice. And if you think about that kind of compared to an acid chloride, an ester is really just a worse version of an acid chloride, or a less reactive version of an acid chloride. And everything that we did to an acid chloride, we theoretically can do to an ester. But the only thing that attacked acid chlorides twice was fiercely strong nucleophiles. And if they can attack it twice, or if they can attack it once, they can just go again. Because it's the first step that's hardest. In both of these cases, with the lithium aluminum hydride, you get the same thing. You get that aldehyde. And so in both of those cases, you get the same thing. So of course they can attack it twice. All right, so esters though, for esters, technically they can get attacked by strong nucleophiles. But largely attacking them with strong nucleophiles is kind of pointless. First off, if you were to attack them with like OH minus, here, I'm gonna ask you guys not to worry about writing this down because it'll probably just confuse you later. We don't do this very much because there's not a lot of point to it, but they can get attacked by strong nucleophiles. So like if I added an OH minus, it can attack, but check out what we would get. You're turning in an O minus for an O minus. What's more stable? It's an O minus either way. So it's not very favorable to do, but we can do it. But it doesn't make a lot of sense to do this. We can, and we can break an ester this way. And it's fine. It can function. And we can do this. So it's something that we can do. They will react with strong nucleophiles. But more often, we do it in that kind of other way, which was the kind of the new way that these esters stand alone is that a lot of our, I'm going to rewrite that part. I think of that OR as a pretty cruddy leaving group. One thing we can do to this pretty cruddy leaving group is make it a better leaving group by adding some acid. Acid will make one of those oxygens into an O+, which is a better leaving group. And if we add O+ and water, or sorry, H+ and water, then we can kick that thing off, that OR, and replace it with an OH. All right, so you can write this down, but you've got it in your notes from Friday already. But check this out. If we start off with this thing in the OH and we add acid, then we make this into a better leaving group so we can kick it off. Well, if we add acid and an alcohol, we'll replace this OH with an alcohol, which adds an OR. So we can make this thing go the other way around with acid and an alcohol. And to add a bonus to this, if we start with either of those things and we add acid and nitrogen, we can make these things good leaving groups and replace them with the nitrogen. So you get this kind of cool triangle here, where if you add an amine and acid, you'll kick off your leaving group and replace it with an amine. And in both of those cases, starting with either of those things, this is what you would get. Biologically, this is how we do all of these interconversions. So in your body, this is how you do all this stuff. You never make acid chlorides. And furthermore, let's complete our other arrows. If you were to start here, how would I get up there? If I start with an amide, carbonyl plus an amine, I want to turn it into an OH, what would I add? Well, I'm going to add my acid to make it a good leaving group. And if I want to add in an OH, what's the simplest molecule to add? Yeah, or water. So notice that water and acid will take either of those guys, esters or amides, into carboxylic acids. Acid and amine will take either of those guys, ester or carboxylic acid, and make it into an amide. And if you start with either a carboxylic acid or an amide, and you want to make it into an ester, you add the acid and alcohol. So the color coding really here, I think, helps. That's how we go backwards. So you really only have two conditions. Oh, wait a second. So if you start with esters, there's only really two consistent good ways to make them react. Either you add acid in whatever weak nucleophile you want, or you add a fiercely strong nucleophile and it'll go twice. That's pretty much it for esters. So let's go back and finish our bridge. Stop sharing, bump it down, share our screen, start. All right, so we'll put these guys in red. All right, starting with esters. So we only have 3 of these esters here. All right, an ester plus a Grignard. A Grignard is a fiercely strong nucleophile. Will it attack an ester? Yes, it'll kick this chunk off. In fact, it'll do the exact same thing as the problem above. It comes in here, kicks electrons up, they come back down and kick that off. So after this first step, notice that whether you were to start with an acid chloride or an ester, a Grignard will treat them the same way. So after the first step, you get the exact same thing, you get a ketone. Will a fiercely strong nucleophile attack a ketone? Heck yeah, it will. So we'll go again, whether we want to or not. Kick electrons up, and you would get the exact same product as the one above. Oops. 2 carbon chunk there, 2 carbon chunk there, and then O minus. So these guys end up being the exact same because Grignards treat esters and acid chlorides the same. All right, scrolling down a little bit. I've got an ester and I add a weak nucleophile with nothing else. Will it react? No, no reaction. All right, but if I add some water with acid, then I will be able to do it. I'll be able to take this thing off right here and replace it with, oh wait, perfect. Exactly so. So all of those are just interchanges. All right. So I know we kind of went slowly on this, but I know you guys have a lot of reactions on in your brains for this week. But put them into these pots. Right? You've got the stuff from Friday, which was mainly ketones and aldehydes react with fiercely strong nucleophiles. Plus, look at what attacks at the carbonyl direct attack versus that alpha beta when you have the enone. For today, we added in acid chlorides, which will react with anything, but fiercely strong nucleophiles twice. And we added esters, which don't react with much. They kind of do 2 things. Fierce nucleophiles twice, same way we did acid chlorides. And then if you have acid, they'll just kind of interchange with anything. All right, questions? So I really invite you to think about that in terms of like 4 buckets of reactions as opposed to just, I don't know, 25 different possibilities. So I'm going to ask you a little bit of review. We don't have a lot of minutes left, but there's one new reaction that I want to talk about, but it's not really new. As if we haven't done enough today. All right, so if I were to start with this thing right here, which is a ketone, and I were to add a Grignard, CH3MgCl, would my nucleophile attack? Yes, because this is a fiercely strong nucleophile. It acts like a CH3 minus. It would attack, ta-da. Add in a CH3. All right, that is not new. All right, also not new from Friday. If I were to start that with that guy and add the Gilman reagent. Anybody remember what the deal was with the Gilman reagent? Okay, Gilman reagent. This is in your notes from Friday. The Grignard is a fiercely strong carbon with a negative charge. The Gilman reagent acts like a normally strong R minus. Do those kind of normally strong nucleophiles attack carbonyls? Going back to our question that we've asked so many times today, what kind of things attack ketones or aldehydes? Fiercely strong nucleophiles. The Gilman reagent was invented particularly because it's not fiercely strong. So will it attack a ketone? No, because what attacks ketones and aldehydes? Fiercely strong nucleophiles. And if you don't have one of those, you're not going to attack. So no reaction. All right, here's why this matters a whole lot to us. If we were to start off with an acid chloride and add a Gilman reagent. So a Gilman reagent is always two of the same carbon chunks with copper lithium, but only one of them reacts. So just pick one, they'll always be identical. And it's just that thing with a C minus. So once again, this is your Gilman reagent. This is just your strong R minus, as opposed to being fiercely strong. Acid chlorides. What kind of nucleophiles attack acid chlorides? Any of them, right? Is this any of them? Sure is. So will this attack an acid chloride? Sure will. So nucleophile attacks an acid chloride. Sydney, how do the electrons go?
They slingshot to the end.
Yep.
Come back down.
Yep.
Pick off.
And you'll only do that slingshot thing if you've got a leaving group. You'll never do it if you don't, right? That's the deal with the whole slingshot thing. You got to have a leaving group. You got to have something to kick off. And so I will kick off this chlorine and replace it with whom? Exactly, that new CH3. All right, you know everything you need to know to answer this question. So think about it. Caleb, what kind of nucleophiles attack ketones or aldehydes? All right, Olivia, a Gilman reagent, is it a fiercely strong nucleophile? So, Sydney, will this C minus of a Gilman reagent attack an acid chloride twice? No, it just attacks once and then it stops. So the Gilman reagent was invented because of the fact that it's different from a Grignard. It does different things. Grignard reagents are fiercely strong. They'll attack an acid chloride once. A Gilman reagent is not fiercely strong. It'll only attack an acid chloride once and then it stops. So if you want to attack once and then stop, go Gilman. If you want to attack an acid chloride twice, adding the same chunk on twice, go Grignard. But we have choices, which is great. Just what do we want to add? All right. How are we feeling?
Much better.
You feel good? All right. Let's, I got 2 minutes. All right, you got 2 minutes. I don't have enough time to do anything crazy. So we're just going to ask a couple more. We're going to review a couple more quick questions. All right, bam, 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 bam. All right, Caleb, it's an ester. If I were to attack this thing with lithium aluminum hydride, what would happen?
It would act the right half would leave.
So lithium aluminum hydride, what is this?
H-.
Right, is it fiercely strong? Yes. So what's it gonna do?
It'll attack on the double bond.
Yep,
And then the electrons with the double bond will slingshot.
they would, yes. Fiercely strong nucleophiles will always attack your carbonyls. They're gonna kick that whole chunk off, and it would replace that whole chunk with what? Right? And are you done? No. So good. So what you did is you didn't try to rely on your memory, you looked at it. And you looked at it, and you saw that this thing is a water.
No, not.
Right, but from the point of view of reactivity, they react basically the same way. You've got this aldehyde now. Can you attack it again? Yes. In fact, you don't get to choose. It will be attacked again because you still have that hydride. All right. Now, what's the mechanism going to look like?
It was back behind, and then electrons would go to the, not slingshot.
But not slingshot back down. Perfect. Exactly right. We will have 2 hydrogens, and then we should do a little step 2 where you add some water to this thing because we want to end up with that alcohol. And look what you've made. You made propanol. Ta-da. And I hear the bells ringing because it's 2 o'clock. So please practice this. I will see you all in lab either this afternoon or tomorrow morning or tomorrow afternoon, or I will see you in class sometime in the future. Thanks. Have a great day. Do, 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 do.